Okay, so we've seen a few program proofs now, but they were basically on sort of, I don't know, little fake programs. Now we're going to go back to our conversion to binary program, which is at least sort of a real program example. And we're going to see how that works for a program proof that to show that this conversion to binary program actually works. One thing I will change about the program is the way I had written it initially, which is maybe the way that you'd write it. I sort of had this n variable, and the n variable kept on changing. What I'm going to do is I'm going to just substitute in a dummy variable temp so that I can leave the n variable unchanged. And then we can talk about what it means to put sort of the original value of n into the array A in binary format. Okay? So, our question is, does it work? And if it works, how do we know? And, we want to do something beyond, well, I tried it on a few numbers and it works. Testing's good, but it doesn't really prove correctness. And what do we mean by correct? Well, it's actually a little bit hard to talk about what we mean by correct, since we haven't really defined what it means to say we're putting a number into binary format within some array A. So let's define that. We can't sort of mathematically say we're going to prove something if we haven't defined what it is that we're proving. So what does it mean to say that we're putting this number n into binary representation and storing it in array A? What it means is, well, first of all, when we say it's a binary representation, we're expecting that all the values of our array A will be either 0 or 1, or binary values. And secondly, we expect it if we interpret each of those values as being, whether or not we have a given power of 2, we expect the summation of powers of 2 to be equal to n, where n is the number we're converting into binary. So we have, if a of 0 is 1, we expect that to represent, there's a 2 to the 0 term within n. And if a of 5 is 1, we'd expect there to be a 2 to the 5 term within the binary representation of n. Okay? If we want to be a little bit more abstract and not even worry about defining x, we can just say, well, let's imagine that we have a full infinite array A. It's initialized to be 0 everywhere. And now if we sum up the terms of this now infinite array A, take them to be powers of 2, they should still sum up to be the value of n. Okay, so now we step back to our program. And we say, what is the loop invariant here? What are we looking for a loop invariant? Well, we're looking for something that's true every time we go through the loop. We're looking for something that's, of course, related to the program variables. An arbitrary true statement that has nothing to do with the program isn't going to help us very much. And finally, we're hoping that by having this loop invariant be true, every time through the program, we want to achieve setting our array A to be the binary representation of n. Okay? So that's what we're looking for here. So I'm going to just throw out a loop invariant. This is a loop invariant that's been suggested in many classes when I actually teach the class live. This is a sort of a pretty good first guess at what our loop invariant is. We sort of expect that, some of the value n is stored in temp, some of the value n is already converted into binary, and you sort of combine these two things to get our n values. I'm going to say, let's imagine that we've just completed our conditional. The conditional holds true, and then just before we get to the loop, we're going to say that we hope that this invariant is true. Okay? So what do? We say, well, loop invariant, we need to do initialization, termination, and maintenance. Let's start with the easy ones, initialization. So let's evaluate the loop right here. Is it true that this statement's true the very first time we get to that loop conditional? Well, that's fine. Obviously, after this first statement here, we expect temp to have a value equal to n. after the next line runs, we expect I to have a value 0. And then is it true that n is equal to this formula here? Well, we should remember A is initialized to 0 everywhere. So this entire summation term is going to just disappear. And we're asking, is it true that n is equal to temp? Well, yes, it is. So that's great. Our initialization is fine. Now we want to check termination. We want to say, if we prove that this loop invariant holds every time through the loop, does it sort of do what we want it to do? Well, when do we exit the loop? The conditional says the loop's going to keep going as long as our temp variable is positive. We're going to assume that temp is non-negative. We're going to assume we start running this program with a non-negative value of n. Maybe that's an assumption that we should have added, but we have a non-negative value of n. Well, the only way that temp ever changes is we do integer divide on it. Temp will always be non-negative. And in order to exit the loop, we have to have, well, temp should be 0. Okay, great. Well, if we have temp is equal to 0, then what happens? If the loop invariant holds and temp is equal to 0, then we have that n equals this summation, which exactly matches what we're trying to prove. It proves that, hey, A holds a binary representation for n. This is exactly what we're trying to prove. So things go good. When we terminate the loop, we'll have proven exactly what we want to prove. So now comes the tougher part. We want to do our maintenance, right? So great. We're going to assume that right after some arbitrary iteration, we're going to assume that our loop invariant holds. Here's our loop invariant. We're going to assume that it holds right after our iteration. And then we're going to say, well, great. How do the variables change during the course of one iteration? I'm going to stick sort of just prime variables to represent things instead of using all the subscripts. So what happens here? Well, we see that our new a prime of I value, it has an assignment here. We have a new temp prime value from our assignment here. I gets changed, and that's all that's changed. There are a couple more variables. N prime equals n. Well, n never changes anywhere in the entire program. And for all of the array values other than the one that's at index I plus 1, or sorry, the one that's at index I, a prime is not going to change. So for every index other than the one at I, a prime is going to be equal to a. Once we do that, now great. Now we have everything we need from the program. We go, great. We have, we're given this. This is our loop invariant assumption. We're trying to prove the same thing holds with primed variables, and we know exactly how all of our variables change. So now we're sort of down to our algebra. So what are we going to do here? Well, first I'm going to plug in for my n prime here. Great, I want to plug in for my n prime. N prime is equal to n, so let's do that. That looks good. Next, well, if I know that the thing on the left is equal to an equation equal to n, and I'm trying to prove the thing on the right is an equation equal to n, really the thing I'm trying to prove is just these two sort of nastier looking terms are equal to each other. So that's what I'm trying to prove next. Okay, I'm going to do that first. Okay, I'm going to sub out my temp prime term. This is just algebra, just substitution, sort of highlighted it slide by slide. You might want to look through those slides a little bit slower if any algebra looks bad, but I'm going to substitute in for temp prime. Great, I can do that. I'm not going to need that anymore. Now I have this, all these a primes are exactly the same as the a terms, except for the one at I, okay? So what I'm going to do is I'm going to substitute in all the a primes to be a terms, and taking into account that, well, now I got to take out this, I still have one new a prime term, and I have one fewer a term. But anyway, this is really just another algebra substitution. We're going to do this. Great. I know what this a prime is. I can substitute in for that. This temp prime. And now I have these two big sort of ugly looking terms, but they're on both sides of the equation. Since they're both on both sides of the equation, I can get rid of them. And now I'm left with this equation. I'm trying to prove that this equation holds. I'm trying to prove that this equation is true. So can I do that? Well, first of all, I don't actually know what A prime is, or A of I. Kind of want to make that term go away. Now, at this point, I sort of realize, oh, you know what? I've actually forgotten part of my loop invariant. When I started this, I assumed that all values of A were initialized to 0. And I'm going to use something that looks just like that as part of my invariant. All values of A at I or larger are equal to 0. Okay? It holds for the initialization because all the A terms are 0 at initialization. And then given that all the A's I and higher are equal to 0, one loop later we just have to prove that all the A's I prime and higher are equal to 0. Well, they're all unchanged because A of I is the only one that changes. And we could sort of do this part of the loop invariant more formally. We'll end up seeing it again, but it's fine. By doing this, we can say, oh, you know what? This A of I term up here is really 0. It really is. So great. Since it's 0, I can get rid of it, and now I'm left with this. I'm trying to prove that this equation holds. Does this equation hold? Well, there's something a little bit suspicious here. We use the fact that A prime is bigger than, or I prime is bigger than I, but we never actually used exactly what is I prime equal to anywhere in our proof so far. It's somehow weird to think, oh, no matter how I is changing, everything's going to work just fine. So that doesn't seem right. If we don't know what I is in this program, and I don't know what 2 to the I is, and just throwing around an arbitrary 2 to the I term sounds a little bit sort of dangerous. And finally, if you think about it, as the program runs, temp keeps on getting smaller and smaller and smaller, keeps getting smaller. I keeps getting bigger and bigger. By the end of the program, you expect 2 to the I to be sort of a big term, and temp is down near 0. If temp happens to be a small, even term, then I'm saying, well, temp mod 2 is 0. The second term goes away. And this, small, even term, is that equal to the same term divided by 2? Probably not. That kind of looks bad. Or even if temp is odd, then I have a small odd term equal to half of that term plus 1 times 2 to the I, or 2 to the I could be quite large. That also looks kind of bad. So it seems like something has gone wrong here. Maybe our invariant was flawed. So we can go back to this. We used 102 as our example when we were talking about conversion to binary to begin with. Let's just sort of walk through what happens if you have the number 102 as n, and you go back to your program. So we start our program, great, n's 102, we set temp to 102, I equals 0. This thing evaluates fine when that goes. Now, a of 0 equals 102 mod 2, that's 0. 102 div 2 is 51. I gets incremented. Now I come back up to the top of my loop. And when I come back up to the top of my loop, I want to ask, is this statement true? Well, let me just plug in everything. Is 102 equal to 51 plus the sum of a bunch of 0 terms? Because A is 0 everywhere, and certainly it is not. Our loop invariant failed one loop into our iteration in this case. So that's not so good. What happens is our loop invariant was actually close. The only thing that we needed to add to it was, well, this temp term needed to be scaled up by a 2 to the I term. It turns out if we add that to our loop invariant, everything's going to go through nice and smoothly. We'll see that. But, I just sort of went through this exercise to show, don't expect that you're going to just guess the right loop invariant correctly first. It's not exactly a guess, but there might be a little give and take here when you're trying to prove something, right? Especially if it's someone else's program. If it's your program, maybe you know why the loop is there and you can formalize it a little easier. But if you're looking at someone else's program and trying to prove something, it might take a while to come to the proper loop invariant. The one that we started with was actually pretty good. The students who tend to suggest that tend to be among the stronger students taking the class. Now, it's pretty rare for a student to suggest a loop invariant like this one. It's pretty hard to come by. Anyway, so we step in here and we go, we're going to add in this 2 to the I term to our loop invariant. We can also add to our loop invariant because we've already seen, well, we should really have these things where we say, oh, all of the large values in the array are still 0, and everything in the array is always 0 and 1. So we're going to add those to our loop invariant to sort of make our proof go through nice and formally. This last part here, all the terms are 0 and 1, I'm not going to talk about it too much. I mean, we could add it to our loop invariant, or I could just say, look, I initialize everything to 0, so it's true to start. And then the only thing the algorithm ever does to change the A values is set them to a number mod 2. Well, a number mod 2 is going to be 0 or 1, so we're not going to go wrong there. This is always going to be fine. So let's step back and go back to our easy ones. Initialization and termination. Okay? Well, this extra part that we're trying to prove, is that true upon initialization? Well, yes, it is. When we start off, all of the A values are 0, so we're going to be fine saying that some of the A values are 0, or all of the A values are 0. Also, when we start, I has the value 2. 2 to the I equals 1. This statement was true before without the 2 to the I term. Multiplying temp by 1 doesn't change. Everything's going to work out. It's still going to be fine. It's still going to be true. Great. Initialization's done. Next, let's go on to our termination. Again, we sort of have the same exact thing as before. When temp becomes 0, 0 times 2 to the I is going to be 0. It doesn't matter what 2 to the I is. This 2 to the I term isn't going to change anything, and we're going to have n equals this big summation term, which hasn't changed. And when n equals that summation, that exactly implies that A holds the binary representation of n. So great. Termination's going to look good. Now we come back to our maintenance. Well, our variables change exactly like they did before. We can also say we have this extra thing. We're trying to show that all the large terms of A are 0. And really, the only thing that's changing is there's something changed in our given, our invariant, and something changed in the thing we're trying to prove. So we step right back into our algebra phase where, okay, we've added this term to our given, and we've also added it to the term that we're trying to prove. Now we're going to go right back through all of our substitution that we did before. Okay? So we're going to substitute in for n prime, turn that into n. Great, we don't need that anymore. Now we have this big equation. It's equal to n on the left. We're trying to prove that something is equal to n on the right. That's the same as just proving this thing over here is equal to this thing over here. So we're gonna do that. We're gonna say this is what we're trying to prove. Next, we're gonna get rid of our temp prime term by plugging in for it. We don't need that anymore. Now we're gonna get rid of all these A primes which haven't changed except for the one at A of I. So we're going to do that. We're going to substitute in just like that before. Great, we've done that. Now I'm going to come back down to this little, oh, I'm trying to prove that all the large A terms are 0. Well, it started out that we were given all of the A of I and up were 0. We need to prove one iteration that all of the A prime of I prime and up are 0. Of course, we can get rid of I prime equals I plus 1. So we're going to plug in for that. We also happen to know that, hey, for I plus 1 and larger, A prime doesn't change. So great. A prime doesn't change. I can substitute in for that. And now, I'm given that all of the A's from index I and up are 0. Prove that all of the A's from index I plus 1 and up are 0. Well, that's easy enough, and we're done. Great. So now I can just use that. I'm also going to plug in this A prime term within back to my invariant, my main invariant equation. I'm going to plug in that A prime equation, get rid of that. Not going to need that anymore. Now I'm actually going to use my I prime. If you remember last time, I kind of finished this whole thing up and had this, never used the fact that I prime equaled exactly I plus 1. Well, here's where I'm going to plug it in. I prime equals exactly I plus 1. I'm going to plug it in there. Great. Now I know that all of these A of I terms, A of K equals I and up is equal to 0, so I can get rid of this A of I term. It's equal to 0, and I can get rid of it. And this is the equation that I'm trying to prove. If this equation, it holds, then my loop invariant holds, okay? So let's look at this equation. Well, first of all, I've got this big, sort of big ugly summation over here, but it exactly matches the big ugly summation on the right, so let's cross those out. Now I notice, you know what, I have a 2 to the I here term, I have a 2 to the I times 2 term here, I have a 2 to the I term here. I can cancel out a 2 to the I term everywhere. And now I'm left with this equation. Is it true that for an arbitrary non-negative integer temp, that temp is equal to temp integer divide 2 times 2 plus temp mod 2? Well, temp integer divide 2 times 2 is exactly going to be temp rounded down to the next highest even number. So if temp is 71, it'll round down to 7. Temp div 2 would be 35 times 2 is 70, or 70 div 2 is 35 times 2 is 70. And then we either add back the remainder in the case of 71, which was 1, or the remainder of 0 if temp happened to be even. So this holds. This is basically almost how we define, integer divide and modulus. This is almost how we define modulus, given it a definition for integer divide. So great, we're done. That is our loop invariant. Our loop invariant holds, and we've already done the termination step. We've already shown that if the loop invariant holds, then at the end of the program, we expect the array A to hold a binary representation of the number n. There you go. We're done with sort of a big proof. Up next time, an in-depth analysis. Taylor Swift, modern day Debbie Gibson, you decide.